effect evaporation system. I'm trying to get back to the screen I'm sharing, and yeah. I think coming to the model, I better share with you another file that appears to be a little bit more organized. But before we do that, let me probably use the whiteboard and show you here the way that we do this kind of balance, because this is something that you'll be doing not only for this, but for the multi-effect desalination systems as well. When we are talking about basically two units, one of them is, excuse my drawing. So these are the two units that we have. One of them is an evaporator, one of them is a condenser. For the evaporator, we bring steam from a power plant. The steam is condensing here. After it condenses, we take it back again to the power plant. So this is basically m dot steam coming at a temperature T steam. We assume it is saturated vapor as it enters here and it leaves as saturated liquid. So we neglect any degree of superheat or degree of subcooling for the steam. So that if we are looking at the energy in the evaporator, we can simply say that it is equal to m dot steam into HFG of steam. So this is the kind of energy N that we have to the system. Then we have seawater, which is basically entering the unit inside the tubes in a shell and tube heat exchanger. And they are heated here from T cooling water to a temperature that we call TF, which is the feed temperature. Then we have mass flow rate. The mass flow rate, we prefer to put it like this: m dot cooling water and m dot feed. It's a whole quantity coming, but the way we put it this way, because here we say that this m dot cooling water will be thrown away back again to the sea at TF, and the quantity that we need as feed is the quantity which is being sprayed here. So this is m dot feed. This m dot feed enters here. It is spraying on the surfaces of the tubes. It makes a thin film over the tube surfaces where it will be heated from T feed to the saturation temperature, which is TB. Part of it is going to evaporate. We have a mist eliminator here to prevent the seawater from being carried with the vapor. And the vapor is going to take this quantity of vapor that has formed and it will come in here. So this is basically m dot vapor. Sometimes we refer to it as m dot distillate. It will condense here and we are going to collect it here as the product. So this is basically what we have in here. If we need to make an energy balance, the energy balance is going to be for the evaporator, as well as for the condenser. So for the evaporator, we have, this is the energy N coming through the steam. And this energy N is going to do two things. Number one, it's going to take the feed and heat it from TF to TB. So there's sensible heating here, m dot feed, Cp of the water, TB minus TF. So part of the energy that has been spent by condensing the steam is going to heat all the feed from TF to TB. And then part of it is going to condense. M vapor into HFG vapor. What is the difference between this HFG and this HFG? This one is at steam temperature and this one is at vapor temperature. Vapor temperature is less than the boiling or saturation temperature or brine temperature by the boiling point elevation. Boiling point elevation, you can obtain this value either through a correlation. You'll find the correlation in the file that I uploaded today, or I'm going also to upload a book. The book is Fundamentals of Seawater or Saltwater Desalination by Hisham al-Dasuqi and Hisham al-Touni, and you'll find that in the second chapter of this book, he's talking about this kind of technology and has given it in details. And in that part, he will be given a correlation, and this correlation is also in the appendix that you can use it to calculate the boiling point elevation. To make things more and more easy, the boiling point elevation is a built-in function in the EES, Engineering Equation Solver. Now, this is the energy balance for the evaporator. Qn, which is given by the steam, is used for preheating the feed from TF to TB and then evaporating part of it. Then, if we are looking at how much is the temperature difference, remember the temperature profile here for the evaporator is basically something like this. We have steam condensing, so it is condensing at a constant temperature. And then seawater is coming here to be heated to saturation temperature, and then its temperature becomes TB. This part of sensible heating here, we are going to neglect. Why we need to neglect it? Because we are looking for a simple way to calculate the surface area. Accordingly, the Q here can be given as the overall heat transfer coefficient. You have tubes where seawater inside. There is the tube wall, and there is, steam inside, tube wall, and seawater outside. So there's an overall heat transfer coefficient that will be calculated here into the surface area. Into, if we consider that both of them are at constant temperature, then simply you can put it like this, Ts minus Tb. If we are going to consider that there is sensible heating here from Tf to Tb, then we have to take this part alone and calculate like a log mean temperature difference in. It's a small part that is not worth the hassle. So that's simply how we can use this Q that we calculated from the mass flow rate steam of HFG steam. U is normally given, you'll find it given in the book as a polynomial function of temperature. So that's easy. Otherwise, you need to go back to the old formula that we have studied in heat transfer, that is 1 over HA on the inner side plus R conduction plus 1 over HA in the outer side plus R fouling if you have fouling there, and calculate the overall heat transfer coefficient in details. But it is simpler to take this formula. It is not 100% accurate, but it's coming with acceptable accuracy so that you can calculate the overall heat transfer coefficient. Ts is known, Tb is known, so you can determine how much is the surface area. So you can estimate what area is needed for the evaporator, and this is what we call sort of a thermal design of the unit. The second unit that we are going to consider is the condenser. And for the condenser, the energy balance again is Q condenser. The energy is coming in the condenser from the vapor, which is there. So m dot vapor into HFG vapor. And we'll consider that the temperature here is the same temperature here. We're going to neglect the drop in temperature due to friction losses and minor losses like bends, elbows. This kind of things we'll neglect because the temperature difference is small. So that will just, for simplicity, take it as is. This is going to be in balance with the quantity of water which is coming, which is m dot feed plus m dot cooling water into Cp into T feed minus T cooling water. So this is the energy balance in the condenser. Now note that I've written the energy balance and I've not yet put relation between the masses, which is basically the mass balance. In the condenser, look at this. We have two separate streams. The m dot vapor enters here and leaves here. It's not mixed with anything. So mass N is mass out in the shell side. In the tube side, we have m dot cooling water and m dot feed entering, m dot cooling water, and m dot feed leaving. So again, there's no point of making a mass balance in the condenser because the streams are separated. We'll only need to make a mass balance for the evaporator. So for the evaporator, the mass balance will be, you have m dot feed coming in. Part of it will evaporate, and the rest will be rejected brine. There's another thing here that we may add to this equation, which is, as the feed comes, it comes with a certain salinity, but the vapor has no salt at all. Vapor is assumed to be pure. It has no salt, which means that the brine is going to leave with higher salinity. So to express that, we're going to say that m dot feed into x feed is equal, the salinity of the pure vapor is 0. So it will be m dot brine x brine. So in the mass balance here, we have two things. One of them is mass balance of the water in the evaporator. The second is the salt mass balance in the evaporator also. M dot feed, this is the feed flow rate, X feed salinity of the feed. M dot brine is normally less than M dot feed because part of it has evaporated. So that the salinity here of the brine is going to be higher. So you expect a higher salinity of the brine, which is being rejected here. So normally XB is greater than XF, assuming that salinity of the vapor is 0, which should be true. We put a mist eliminator to make sure that the vapor is going to leave without any salts at all. So back again to the condenser. This is the energy balance in the condenser, and this energy balance is equal, the Q is equal to U in the condenser. The overall heat transfer coefficient written here was for the evaporator. Here is the overall heat transfer coefficient for the condenser, surface area of the condenser into log mean temperature difference. Here it cannot be a simple temperature difference as we did in the evaporator. Why? Because in the condenser, yes, one of the streams is at a constant temperature, which is TV. But the other stream, which is the seawater, is going to increase in temperature. So this is T cooling water, and this is T feed. So we have a delta T1 here, a delta T2 here. So delta T2 minus delta T1 divided by ln delta T2 over delta T1 is the log mean temperature difference. Now, what you see here in front of you in this slide that seems a little bit crowded now is all what we do for mass and energy balance. This is the thermal analysis of a single effect evaporation system. What we need to do is take this into an example and solve it. Has the book done that? Yes, it has done that, but it has done also a lot of algebraic manipulations, which are not needed to analyze the problem. But he did it for one purpose. He wanted to come up with an expression for the system performance. When we are talking about system performance here, in thermal systems in generally, which are operated by steam, we have a way that we calculate the performance. And calculating the performance here can be done by, we have already been exposed to the GOR. We know what's the GOR. For our case, or in general, the GOR is m dot vapor or distillate into HFG of the vapor divided by Qn. In our case, What's Qn? What's the energy input to the system? Who can tell me?
For the evaporator or the
Where's the external energy is coming to the system?
mass of the steam to the
Steam. Exactly, it's steam. So it should be m dot steam into HFG of steam. So this is basically is the expression of the gore for the system. And this is why they have used another system or another parameter that is used for evaluating the performance. And this parameter is called performance ratio. And the performance ratio here is basically m dot vapor over m dot steam. This is a constant, and this is another constant. So more or less, the performance ratio is going to change by changing how much vapor the vapor is whatever is going to condense. So it is basically m dot distillate over m dot steam. And this is our performance ratio. And from now on, we are going to rely on the performance ratio a lot, as long as we are talking about conventional desalination systems. There's something here I have to tell you, that there is a difference between us here in the academia and the industry. In the industry, they switch those values. They say the gore is m dot d over m dot s, whereas the PR is given by that expression. I mean, that's in our belief, that's not the way it should be, because we needed the gore to be more general. It applies to single effect evaporation, it applies to HDH system, it applies to solar still where there's no steam at all. So the point is the expression of the gore is more general than the expression of the PR, but it's just a non-standardization of the terminology which is being used. So at the end, we are looking for some parameters that we are interested in to indicate the performance. So if we are going to talk about performance parameters, definitely number one will come the PR. Maybe you can talk about the gore, because both of them are very much related. We are looking for how much cooling water is coming to the system, because this means what should be the size of the pump that will bring the seawater from the sea, and that affects the capital cost of the plant. And area of the condenser and area of the evaporator. If we divide this by m dot distillate, this is what we call SA, or specific area. It's not only this, but even specific mass rate of the cooling water, which is m dot cooling water per m dot distillate. So at the end, the three parameters that we rely on to evaluate the system performance, we are talking about performance ratio, specific mass flow rate of the cooling water, and specific heat transfer area. This is related to the capital cost of the unit. This is related to both capital and running cost, because capital cost in selection of what should be the size of the pump, and running cost is but how much energy this pump is going to consume while operating. And this is a performance parameter. If the system is operating, then how much is the PR? The PR for a system like single effect evaporation is somewhere in the order of 0.97. So basically you are close to 1, which means that back of the envelope kind of estimation, you need 1 kilogram per second of steam to produce 1 kilogram per second of desalinated water. This is a performance that we don't like. Why? Because in the industrial systems for mass production, we have the MSF, multi-stage flash desalination system, and the PR for these systems is close to 10, meaning that you use 1 kilogram per second of steam from the power plant and produce 10 kilogram per second of desalinated water. Or the MED, multi-effect desalination systems, where the PR can reach up to 16. So you are using 1 kilogram per second of steam to produce 16 kilogram per second of desalinated water. That's why, compared to these, the performance that we have here is not really encouraging, but if you remember, we said it has some limited applications that this is used in, like in marine units, in ships where you need to produce water, not too much water, so you just use a single effect system and operate it for your use, basically for people for drinking or so. The question by Khalid will be, would the performance be better if the total mass rate entered the evaporator? The question is no, and I'll tell you why not. In the evaporator, what happens, Khalid? Let's look at this again, to the sketch again of the system. And we have here, in the condenser, what is going to enter will be m dot feed plus m dot cooling water, and then this is going to leave here. If we take all this quantity, m dot feed plus m dot cooling water, to enter into the evaporator, and you need to evaporate all of this quantity, you can imagine how much steam that you are going to need here. It will be a lot of steam, which is going to generate a lot of vapor. When this vapor comes in, this quantity will not be enough to condense it all. So always you are going to need more water in, just to make sure that you condense all the vapor that is formed here into sweet water. And then definitely you'll have to throw something away. I hope I answered your question this way.
Yes, doctor, thank you.
Now, the thing, whatever I showed you here in the slide can be shown in a better way in another document, which is already posted in Blackboard, talking about the single effect evaporation. And this is a sketch of the unit. And here I'm talking about the process parameters, description, how it happens. And after that, I'm given the mass balance equations. M dot feed is equal to M dot distillate plus M dot brine. This equation number 1, is going to be with us from here up to the end of the term. This is always, in every desalination system, we are going to repeat this expression again. This is the salt balance, X feed, M dot feed is equal to XB, X brine, M dot brine. These equations number 3 and 4, they have no added value. They're just manipulation of equations 1 and 2. I'm just eliminating M dot feed and solving in terms of M dot brine, or eliminating M dot brine and solving in terms of M dot feed. That's it. So equations number 3 and 4 have nothing new. They are only some sort of a reorganization of equations 1 and 2. That's why I don't give much of attention to these questions, because there's no because there's no addition here. The energy balance, this is the QE in the evaporator, which is coming by the steam condensation that does sensible heating of the seawater from TF to TB, and then evaporation or latent part. In the condenser, vapor that will condense is going to preheat all the water coming in from the sea, M dot feed plus M cooling water, from T cooling water to TF. And sometimes they are written like M dot feed alone and M dot cooling water alone, but again, it's not new. There's something new here. Then you can do, if you want, an overall energy balance. Sometimes we tend to look at an overall energy balance for the unit. What I mean by that is, sometimes you consider your evaporator and and your condenser and basically do some sort of an energy balance for the whole thing. Like this is the evaporator, this is the condenser. Then sometimes you say that I need to make a control volume over the whole thing and look at what will be crossing the system. Steam will cross the system to condense here and then get back again. Seawater will cross the system as it enters here. So we have m dot cooling water plus m dot feed. When it heats up, the m dot cooling water will be thrown away alone. And the brine will be crossing the system out. The vapor that will form here is going to enter here, so we'll not feel it crossing the system. And there is the m dot distillate leaving the system. So sometimes you focus only on that control volume and see what crosses the control volume. M dot steam crosses the control volume in and out. M dot brine is rejected, it crosses the control surface. M dot cooling water is crossing the rejected here, crossing the system. M dot distillate is leaving, this is our product, and then M dot cooling water and M dot feed are coming in. So sometimes you need to associate each one of these masses with its enthalpy. So the energy in for the whole system becomes M dot steam Hg, M dot cooling water plus M dot feed into their enthalpy, which is Cp into temperature. These are the inlet streams, whereas the outlet streams are four. Steam as saturated liquid, HF, brine leaving here, cooling water thrown away here, and distillate, which is collected here. So we have two inlets and four outlets. Why are we doing that? The ones or the analysis that I did a while ago was not enough. Actually, it was enough. But the point here, we are doing that for another reason. The other reason is we need to come up with an algebraic manipulations, as you will see here in these expressions that you see. All of these, by the way, are not adding anything to the unit. This is just you are doing algebraic manipulations, again, by combining terms together. I want you to go through this in details, read it. You will not need much of this kind of details, but they are interesting to look at because at the end, the author wants to reach to this expression. He wants to bring the PR as a function of the rest of the parameters. He wanted a closed term expression for the PR. Do we need that in our analysis? As I mentioned, the answer is no. We'll not need it. You don't have to do it. But this is something just for your information, that there is a way that we can estimate the performance of a single effect evaporation unit through the utilization of a single factor, which is this, a single equation that gives you PR. The problems that we are going to consider and solve do not have this kind of expression. I don't recommend memorizing it, but I would rather prefer that we go through mass balance, energy balance, and then solve the problem step by step. As we'll see in our next class, inshallah, we will have a numeric example to solve it. But anyway, just to complete the picture so that you would know that that's something that can be done, I'm putting this analysis here in details. So just follow this analysis. It's not worth talking about it in class. You can just read it in your own, and then you will see that, yes, for the single effect evaporation only, you can come up with expression of PR, expression for the specific mass rate of the cooling water, and then this is a standard way to calculate the surface area. Again, you don't need to memorize this because we'll be doing it step by step. Energy balance for the humidifier, for the evaporator, it will enable us to calculate the surface area as it is from here, and something similar in the condenser where you calculate the overall heat transfer coefficient, the log mean temperature difference, and then you estimate how much is the surface area in the condenser. So this part here, which is basically starting from equation number 7 onward, It's just something which is additional thing that you will not need in analysis of the problem. This is just showing you for people interested in the mathematical model that you can have some sort of manipulations added ترتيب للequations in a way that you come up with a closed form expression for the performance ratio, which is this, for the mass flow rate, specific mass flow rate of the cooling water, and for the heat transfer area of the evaporator and the condenser. Just to make sure that everyone's still with me, would you please all press on the hand raising expression, the hand raising button?
I'm trying to.
Yes, okay.
Where is it, doctor?
It should be at the bottom of this of the participants' names, Sultan.
Okay, wait. Okay, yes.
Found it?
Okay, yes.
So can you press again? Okay, fine. Basir Yahya pressed it already, and Badr? Rashid?
Just a minute, doctor.
It's okay, خلاص. It's okay, I'm just checking in here. خلاص. At least to know it, ya Rashid, so that if you have a question later, you can raise your hand. So just try to locate it and press it then. So that would be it for our class today. And you can leave as usual. If somebody had a question, just I'll be here for about a few minutes more. And please note that my office hour is almost every day except Thursday. You can find me on MS Teams. When you get to there is a course shell in MS Teams for this subject for ME 460. And why MS Teams? Because it's easy there. Once you get there, you can be able to write to me, to talk, then I'll be hearing you. So always at 1 o'clock, I should be there between 1 and 2 o'clock in most of the days. So Sunday, Monday, Tuesday, Wednesday. And definitely, if somebody had a question, you can still email me. I'll be responding to you. But if you want to see me as an office hour and you have a question that needs to be discussed or anything, then we can do it on MS Teams at 1 o'clock, inshallah.
Doctor,
Fadda.
have we decided when is the midterm will be?
I think it is there. We agreed upon a day, and I updated the syllabus in the Blackboard. I think if we get back to the syllabus in Blackboard, we should be able to see it.
I might missed it yesterday because I checked it and did not find it.
I remember I have updated the syllabus, and since we agreed upon a day, so I just put it in there. That's why the syllabus here you'll find between brackets updated. And I'm trying to open it now here in front of me to see the date has been specified or not. Oh, I updated in terms of the breakdown of the grades. Then if you don't find it here, you may look at announcements. Do we have it there as respond to links, distribution of various grades? Yeah, I do remember we talked about somewhere in 21, I remember it was 21st of October. That's what I remember that we agreed upon earlier.
All right. So 21.
Okay. 21 of October, yes, inshallah. Let me put it here for you as a reminder so that you can see it in front of you.
Yes, please.
So it's agreed, doctor, to be in 2021, right?
Yes, 21 of October.
No changes.
No, because we did that based on no conflict with other subjects. That's why I've selected this day.
Cool, thank you.
Okay.
Hopefully there is no conflict, doctor, because when you upload the take the survey you ask us to upload the major dates. Some of us haven't registered yet, and so
Yeah, having registered means that either the dates have not been specified in other subjects, which is something I cannot help it. I mean, I cannot wait for all the subjects to be determined.
Sure, yeah.
Taking our role. Now, if somebody has a problem, then he can consider the other subject then.
Right. All right. Thank you.
Keep on changing and changing and changing this way. And we don't have to do it in the class time, by the way. That's something that probably we can, just to have more time, we can agree and have it in the evening or so. That would probably make it more convenient, inshallah. We'll talk about that maybe a few days before the exam.
One
So
more
if
question, doctor. Could you please upload the solution of homework one?
yes, I will.
Thank you so much.
Inshallah.
Appreciate it.
You're also welcome.
Doctor, so what
Yes.
will be the content of the midterm chapter?
What will be what?
The content of the
Content,
midterm.
yes. We have the solar stills, we have the HDH systems, and we have the single effect evaporation that we are talking about now. By the time we reach to the exam, probably we could have covered the MED as well. It's coming in something like it's almost a couple of weeks. So yeah, I guess part of the MED, not all of it, is going to be a part of it as well. I'll just make sure that the part that will be in the exam will be the part that we cover in the class, and you already have a homework on it, so that you have enough practice on the problems before coming to the exam.
Okay, thank you.
You're most welcome.
Doctor, about the video, the class video.
Oh, yes, you reminded me. I have to take care of it today, inshallah. So I'll try to find a way that the videos are there and the links provided to you. As I told you, I had to remove it from because we have a limitation of the storage on the cloud. So that's something I'll try to find a venue to put them all in so that they remain for you for the rest of the term, inshallah.
I think, Doctor, if you put them in the zip file and put them in the Google Drive, it will be okay.
Yeah, it would be, but still the Google Drive has a certain limitation. You cannot dump. The files are large. The video file for each lecture, it's something that exceeds 200 megas. So that's an issue that you can, in 5 classes, you can reach for 1 giga. So I'm not sure how much is the limit that I have in the Google Drive. I will verify that. So I'll try to find a way and share it with you. So I'll keep in mind that Google Drive could be an option, and I will see.
If you put them in zip file, maybe the size will be smaller.
It depends. Some files are very well compressed. Some files are not. So I will study that definitely. I will be looking into it and put it soon to you.
Okay, thank you, Doctor.
You're most welcome.
Doctor?
Faddal.
I have a question regarding the first quiz.
تفضل عبد الكريم.
Okay. The question is about the GOR. The GOR. Okay. So
Yes.
I believe there was a mistake there. Can I resolve it?
A mistake in what? Actually, the problem on the GOR, I don't think anybody has got it correctly. The only issue there is related to the units. If the units are adjusted, then things will be okay.
Yeah.
When you are looking at the GOR generally, then you'll be looking at, I'm trying here just to bring a white board again, and GOR, it has to be m dot distillate HFG divided by QN. The m dot distillate has to be in kilogram per second.
Which is what? No, I'm sorry. Which is mass flow
This
rate.
is mass flow rate. HFG is kilojoule per kilogram, which means that the numerator here is supposed to be given in terms of kilowatts.
Kilowatt.
And the QN also should be given in terms of kilowatts so that you can adjust it. When we are talking about a solar still, the m dot distillate is quite small. So the value here is too small. And accordingly, the GOR is expected to be in the order of 0.0002 or 2 or 3 or 4, depending, because everyone has different numbers compared to the other. So you'll find that the value of the GOR is too small. I saw values like 0.2 or 2.5, which is not possible. Which means that basically it was an issue of the unit. As I told you that most of you did not get it correct, so the question which is related to the GOR has been cancelled in the quiz. I did not consider it.
You cancelled it?
Yeah, I cancelled it.
Okay. Okay, can I know how much I got in the written one?
If you open the quiz, you don't see that?
No.
You should be able to see it.
I can see only the final point.
Final grade, you mean?
Yeah, the final point.
I think if you click on it in the page where the quiz is, the link of the quiz, it will take you there.
Yes, if you لو يروح يعني migrate ويضغط على الكويز يظهر.
لا مش migrate، لا مش migrate. لما بتدخل على البلاك بورد نفسه.
ايوه.
في الصفحة الأولى من البلاك بورد، يعني شوف هنا I'm sharing black board here. لما أنت عندك في الستودنت فيو، لما بتيجي للصفحة دي هنا وبتضغط على الكويز، it should show you your quiz.
Wait a minute.
يعني when I click it here, it tells me to start, which means that I can, as if because I did not solve it on the blackboard. So this is how the quiz looks like. So that's why I believe if you click on it, you'll be able to reach there.
Okay, so the information I can see is the number.
Try it there and tell me. يعني جربها وقول لي المرة الجاية. Could you reach it أو حتى ابعت لي إيميل. Could you reach it ولا لأ؟
Yes, I can reach it, and it still saying that needs grading.
Yeah, I mean it's already been graded. That's fine. But أنت بتشوف الحل بتاعك ولا لأ في
أيوة أشوف أي.
يعني الحل بتاعك أنت بتقدر تشوفه. يعني معنى كده إن لو حطيت لكم السولوشن بتاع الكويز you can verify.
لا مش يعني بالضبط اللي أنت تقول عنه.
يعني أنت لما فتحت الكويز أنت شفت how did you solve it?
Yes, no, I can see only how much point I get per
each
question.
problem.
Yeah.
So you don't see which selection that you have made?
Yes, I cannot see which.
خلاص خليني أشوف if I can find a way to download it and send it to you, I will.
Okay.
Just check.
Okay. The written one. How much point it weights?
خليني أفتكر عبد الكريم. I need to get back to the quiz and see how the grade was. was given there. Let me see that. Quiz 1. Do you have the grade? هي مبدئيا كل واحدة منهم ليها 10 points.
ايه
وبعد كده I'm collecting the points and I'm normalizing it. يعني it should be out of 50. وانا بشوف out of 50 how much is it، وبعد كده I put it out of 10 كأن كل مسألة منهم عليها درجتين.
ايه، لان الرساله اللي جتني هي out of 60.
لا لا لا
مش
it's not right. It's out should be out of هو 60 لأن هنا البرنامج is adding them together.
اها
So get out of 50 وبعد كده I normalize it to be out of 10. فالدرجة الموجودة it's out of 10.
ايوه
تمام؟
تمام.
اوكي.
طيب دكتور اذا عندك يعني الوقت اقدر اسوي لك شير سكرين واحل لك السؤال بخصوص الجي او ار، بس علشان انه يمكن يجيني في المستقبل هذا السؤال.
I will share it with you يعني I will put the solution for you بعد كده قارن يا عبد الكريم شوف.
خلاص مو مشكلة.
تمام؟
تمام، الله يعطيك العافية.
الله يعافيك يا عبد الكريم، شكرا.
إذا رسل دكتور
اتفضل يا صالح، معك اتفضل.
في سؤالين دكتور. السؤال الأول ذكرنا في ال HDH سيستم إن الإير موديفايد راح يكون أفضل من النورمال.
افضل من النورمال اير هيتنج سيستم، نعم ده صحيح.
طيب وش اللي يخليه دكتور بحيث إنه إحنا راح نسخن الإير بعد ما يمر على الماء؟
انا هقول لك ليه يا صالح. يعني خليني برضو تاني اعمل شيرنج للصفحه اللي هي البلانك سكرين. بص يا صالح، لما يكون عندي هنا HDH فيها نورمال اير هيتنج، يعني عندي الاير بيدخل على اير هيتر الاول، وبعد ما بيطلع من الاير هيتر بيدخل على الهيوميديفاير. خلينا نقول مثلا ستيت نمبر 1 هي بتاعت الهواء في درجه حراره الانفايرمنت، وستيت نمبر 2 بعد ما عديته على الهيتر، وليكن عديت الهواء على مثلا سولار كولكتور سخنوه لدرجه حراره مثلا 90 درجه. كويس؟
تمام.
بعد كده الميه هنا از بين سبرايد، الميه ما تسخنتش، فالميه عند درجه حراره سي مثلا 30 درجه. الميه is flowing down where air is going up. اللي هيحصل للهواء هنا ايه في الهيوميديفاير يا صالح؟ درجه حرارته هتزيد ولا هتقل؟
راح تقل.
هتقل، يبقى بيحصل عندنا كولينج and humidification. Practically speaking يا صالح، عادة اللي بيحصل لما بتدخل الهواء واتيفر درجة حرارته وبتخلطه المية بيخرج بره عند درجة حرارة المية. يعني الهواء هنا هتكون درجة حرارته بالكتير مثلا 30 35 درجة مئوية. الدرجة دي قليلة قوي. كمية الفيبر اللي بيشيلها الهواء هنا قليل. إذا كون إن بيحصل له كولينج وهيوميديفيكيشن ده حاجة عكس اللي أنا عايزه. أنا مش عايز يحصل له كولينج أبدا، بس هنا we have to do it this way. أوكي؟ طيب إيه اللي ممكن يحصل لو عكسنا؟ يعني لو حطيت الهيوميديفاير هنا وبعد الهيوميديفاير حطيت هيتر، والهواء السخن اللي من الهيتر هنا دخل عشان يحصل له كوندنسيشن هنا. الهواء اللي داخل للديهيوميديفاير هنا داخل عند درجة حرارة 90، هيسخن المية. هيسخنها لدرجة حرارة كام؟ رافلي 60.
60.
يبقى المية هنا بتترش عند درجة حرارة 60، والهواء اللي داخل هنا داخل عند درجة حرارة سي 30. هيحصل ايه للهواء؟ هيتنج وهيوميديفيكيشن. يعني هنا درجة حرارته هتكون أعلى من درجة الحرارة دي. إذا هيكون عنده القدرة إن ياخد أكتر ووتر فيبر، وبالتالي what will condense here is going to be more.
الحين تمام، لأن أنا لو يوم أحللها ما اخذتها يوم بعد ما جاء اللي هو عند 30، اخذتها انه جاء مثلا من البدايه، فبيكون ما يعني درجه حرارته قليله والماي ما صار له هيت، فبيكون اثنينهم باردين، فبيكون
لا، اللي بيحصل بعد كده ايفينشولي انت بتتكلم على سايكل، فاتس كونتينيوس، وبالتالي الهواء دايما عند درجه الحراره العاليه دي هيبتدي يسخن الميه افكتفلي، ودي اللي هتسخن لنا الهواء. So it's sort of an indirect heating للهواء عن طريق الميه اللي هي الهواء سخنها، يعني هي لفه شويه بس. This one should be better than this one in terms of goal. واضحه كده؟
واضح.
طب ده السؤال الاول، ايه السؤال الثاني؟
السؤال الثاني في الهومورك دكتور، في البليت، الابزوربشن بليت، كنت تحط الكيو لوس عباره عن كيو ان،
انت
فوين بيجي بالضبط
بالشكل ده؟
الكيو؟ ايوه
كويس. في المسألة دي أنا في عندي هنا في absorption plate.
تمام.
absorption plate دي ممكن تكون هنا على السيرفس موجودة، بيدخل لها Q، عندي irradiation، وعندي هنا تاو جلاس، وفي ووتر ماشي عليها، فعندي تاو ووتر كمان.
تمام.
يبقى الانرجي ان ليها عبارة عن G multiplied by the area multiplied by tau glass tau water، وهي نفسها ليها alpha for absorption alpha plate. So دي الانرجي ان.
تمام.
طب الانرجي اوت بتاعتها عبارة عن ايه؟ عندي Q losses to the surrounding من هنا. ممكن السطح ده يكون insulated فيقلل اللوسز شوية، بس هيكون عندي losses. وعندي Q by convection to the water. عندك بليت سخنة والبليت دي بتعدي عليها مية، فالمية is absorbing الوتر منها. وبعد كده الانرجي ستورج اللي هي ام ماس بتاعت البليت سي بي بليت انتو دي تي بليت باي دي تايم.
تمام. هذا بس في التصحيح السؤال الاول اتوقع
تاني سؤالك تاني.
في السؤال الاول، وكان السؤال حول السؤال الاول حطيت لي في الكيو اوت كيو لوس كيو ان كيو لوس زائد كانت
انا مش سامعك كويس، وضح لي تاني يا صالح. وات يو مين؟ السؤال الاول في الهوم وورك ماله؟
تمام. في اللي هو الاي ستورج حطيت زائد كيو لوس
لا،
كتصحيح.
في التصحيح حطيت لك مزود لك كيو لوس على الاستورج، مش ممكن يبقى في حاجه مش مظبوطه. خلينا ارجع عليها بص اشوفها تاني، يعني
طبعا
اشوف.
في الوتر هذا انا صار عندي اشتباه، مو في الابزوربر بليت، في
لان
الوتر.
يمكن ما فيش ابزوربر بليت، وبالتالي في لوسز من الواتر. لو انا عندي سيستم ما فيهوش ابزوربر بليت، سولار ستيل مثلا بالشكل ده، وعندي الميه هنا على طول، وما عنديش ابزوربر بليت، فاللوسز هتبقى خارجه من الميه على طول على بره عن طريق اوفرول هيت ترانسفير كوفيشنت في الاريا في تي ووتر ناقص تي سراوندينجز، تبقى دي اللوسز اللي عندي. ما عنديش ابزوربر بليت هنا.
انا خليته فيه، بس اتوقع انه موجود في السؤال، بس يعني كله واحد. المشكله انا ابغى التصحيح يعني عشان في مستقبلا في الاختبار.
لا، لو كان كده ابعت لي، يعني قول لي ابعت لي ايميل.